What's up, everybody? Today we're going to talk about some LMIs and some theorems, lemmas, corollaries regarding LMIs, especially their use in control analysis and synthesis. And because these are the type of techniques and tools that we are going to be using whenever we design some type of controller, especially H infinity type of controller, these type of techniques are used regularly, so it would be nice to get ourselves familiar with these tools and video techniques. And so let's state the lemma. Let P, Q, and H is symmetric, be given matrices of appropriate dimensions, and NP and NQ be the right orthogonal complements of P and Q respectively. I'm gonna talk about what right orthogonal complement means in a second, and let's move on. Then there exists a matrix X such that this inequality, right, and implies this inequality, and also this inequality implies this inequality. So there is an if and only if relationship between those. All right, so we have P, Q, and H is symmetric, and NP and Q can be calculated using P and Q, given P and Q. And so we also know in a way NP and NQ. All right, and the theorem is the following: there exists a matrix X such that this inequality, if and only if these two inequalities. So first, you might realize that this I can see X in this given inequalities. So that is the reason why this lemma can be stated as variable elimination LMI. Sometimes in some LMI textbooks you can see that. And so let's focus on the lemma, and we will try to prove that. Since this is an if and only if, let me get my color right. And all right, first, I'm having a problem with my pencil. All right, let's say this is something, this is a condition, that we like to prove. However, there is another condition, and that implies the condition that we want to prove, right? And in that way, in that case, this condition is known as sufficient condition. And if the condition that we want to prove implies condition, that condition is known as necessary condition. And just wanted to restate that. So let's talk about what right orthogonal complement, that terminology means. It's kind of like null space in a way, and whenever we have a matrix, right, because NP is located at the right of the P matrix, so we have a matrix P matrix, and there exists such matrix N, and it gives zero matrix. All right, so it complements, right? Basically, it's like perpendicular type of relationship is being given here. Let's continue. So this is a technical term, not that significant, and or not that hard to understand. So the lemma can be stated here. There exists X, there exists a matrix X such that, this means such that, and this relationship holds. So we want to prove that. So we want to prove we have condition and we have another condition. this condition implies that condition. Okay, so we want to prove that is the case. So first we want to prove that condition implies, first condition implies the second condition. We will try to prove that, and then when we're done, we will try to prove the second condition in fact implies the first condition. Okay, this is the proof structure whenever we're, especially when we're dealing with if and only statements, right? Okay, so this is called necessity, right? So let's try to prove necessity condition, and will be the easier one. All right, so first condition implies second condition. So this is first condition and this is second condition. What we are going to do is, we know that this condition is correct, and by using algebraic manipulations and other known facts in this specific problem, we will try to derive and obtain, right, construct this second condition. Okay, if we are able to do that, we will say, okay, necessity is problem. Okay, and we will assume that this is the same idea is stated here. First condition is true, and we will try to derive the second condition. Okay, so I just written the first condition, and you know what that means. This S or sim operator means A plus A transpose. Okay, so let's explicitly state that. All right, let's play and post multiply this inequality with NP. Right, this is what we have, and let's organize the terms. Let's distribute NP terms. Right, this looks like similarity transformation, especially orthogonal similarity transformation. So in a way, that is a type of transformation, right? And let's highlight the terms that will be significant. Why? Because P times NP, let me just show that P times NP equals 0, because NP is the right orthogonal complement of P matrix, right? Okay, so this is 0. This is 0. And we also organize this term. Okay, this is 0 and this is 0, and this term is the only term, and we multiplied with NP, right? And we could have done the same thing by using NQ, and by using that type of manipulations, we were able to prove this first condition, let's say first condition, and by using NQ instead of NP, we will be able to prove the second condition. Okay, so this is relatively easy. So that was the necessity condition. All right, let me check, and let me check my. Okay, there's no problem. Right, let's continue. Sufficiency is a thing that we are going to prove now, and first condition implies second condition was a necessity, and the second condition implies the first condition will be sufficiency, and we will assume that the second condition is true, and by using algebraic manipulations, we will try to construct the first condition. If we are able to do that, then we're going to say sufficiency has been proven. Okay. All of them. Okay. So, and the same idea is stated here. So let V1 be a matrix whose column vectors are an arbitrary set of base vectors of this expression. Okay, this might sound complicated, right? But I'm gonna clarify it in a moment. Then there exist matrices V2 and V3 such that these given two like relationships hold. Okay, so let's focus on that. Focus on the first expression, and this basically means, okay, this might sound complicated, but whenever you see that, and basically states that V1 and V2 in a way is in null space of P. So what does it mean? What does it mean is that is the following: P times V1 and V2. Let's consider V1 and V2 of a larger matrix, and that matrix is partitioned as V1 and V2. This is equal, okay, this equals zero matrix, right? Because V1 and V2, they are in the kernel space of P, right? Or null space. Okay, and so that basically means the idea that I just stated. And the same goes with Q matrix and V1 and V3. This equals 0. So, right. However, 0, and let's say Q is n by n. Since let's say this is a one column and this is another column, right? And this is, let's say, 5, right? And this is one column, this is another one column, and this is not 5 by 5, right? This is 5 by 2. So what I mean by that is that this matrix is not NQ, like in this form, right? Okay, for it to be NQ, we need to expand that by stacking some zero vectors. Okay, I feel like that was the easiest thing, and I kind of made it, I don't know, complicated by just stating in a stranger way. So, okay, let's consider Rn space, right? And by looking at this expression, and by the way, this first sentence states that, right? V1 be a matrix whose column vectors are an arbitrary set of base vectors, and vectors of a set of base vectors of like intersection of kernel P and kernel Q. Alright, so what does it mean is the following. Let's imagine Rn space, right? And let's imagine the two sets, the following sets, kernel P and kernel Q. Okay, V1 is in the space that is the intersection of kernel P and kernel Q. Alright, and V2 is in kernel P but not in kernel Q, and this now it sounds like a, I don't know, simple set theory type of subject. And V3 is in kernel Q but not in kernel P. All right, and if kernel P union kernel Q is like doesn't span Rn, and there will be some space that we need to span, right? And that, I think, the residual space will be spanned by the column vectors of V3. I'm sorry, V4. Okay, so the idea basically is that it can be stated here. All right. So, and this idea is stated here, right? And we have a larger V matrix that's partitioned as given here: V1, V2, V3, V4. All right, and we have constructed that V matrix such that that is square and non-singular. And non-singular in that way means like V1, V2, V3, and here looking at this, and V4, they span Rn basically. All right. So that's why it is square and non-singular. Right. And so this expression holds if and only if, right? Since this V matrix is square and non-singular, we can just like pre and post multiply it, like transform it by using this V matrix. Okay. Okay, this is the term that we have. And so at this point, it is beneficial for us to restate what we are after. So we will assume that here, this is first condition and this is second condition. We've proven first condition implies second condition. And now we are going to prove second condition implies first condition. We know this condition is to be true. And that is the second condition. And what we are trying to achieve is to, by using algebraic manipulations, we are going to reconstruct the first condition. If we are able to do that, we are going to say sufficiency is proven. All right. And so let's restate what we are after. And so we will assume that second condition is true, and we will try to derive this. You can notice that since this term, right? This term is here. And what we are trying to do is that, let's say this is 1 and this is 3 and this is 2. We are trying to prove 2 implies 3. Basically, that is the like general idea. Okay. So by using this, we are going to try to reconstruct this condition. Okay. Noting the structure of V, we have these expressions, and this directly follows from the structure of V, right? Here you can see, and let me just show that. Where was it? Like E, V1 and V2 equals 0, right? And by looking at the, so let's partition the 0 matrix. Okay, that is what we have. That is what we have. And however, V3 and V4, they are not in kernel space of P, so it is probable that when we multiply it, we will have like some terms other than 0, right? Okay, so that basically demonstrates that idea. And the same goes with Q matrix. Okay, and remember Q, V1 and V3 is 0 0. Okay, and this is, and the structure of V is V1 V2 V3 and V4. So this term gives 0 and this term gives 0 by using this expression. We've written that. Okay, let's move on now. Okay, so the first term in the like general inequality is written as here explicitly, right? So we transform H by using V matrix, which is square and non-singular, meaning invertible, and explicitly this term is written here. And since H is symmetric, okay, this matrix is also symmetric. So okay, we have done nothing. We just expressed H, or the first term in the inequality, explicitly, right? Okay, let's move on. And P1 and P2 and Q1 and Q2, like, or it would be better to state like separately, this matrix, but since its structure, this matrix is full rank, and this matrix is also full rank. Okay, we know that, like, so far these are the things that we know, right? This is not the assumption that we're making right now. This is the fact that we know, which is given in the problem. Okay, so this is for rank and this is for rank. So X matrix, right? And so you can consider this as a type of transformation. X is being transformed by using these two matrices. Okay. In a way, like for example, we're familiar with the idea of similarity transformation, right? And there are other versions of similarity transformation. And so this is kind of like that. And the transform X is stated as Y, and X Y matrix is also partitioned as here, as given here, right? Let's move on. Then, according to the definitions of matrices P1, PQ, Q1, and Q2, it follows that, and this idea basically states that this matrix doesn't have a null space, meaning it is full rank. Okay, so like informally we can state that. Therefore, for arbitrary y, whatever y matrix you give me, I can find Duan X. Why? Because like this is like, let's say this is X transpose, and we are doing some type of transformation, right? And then we have Y. So there is no information is being lost in that transformation. This is the transformation, right? And whenever Y you give me, I can get you an X. Okay. That is it. That is it. Like this is a transformation, right? And let's continue. Let's substitute the first term in the inequality with its explicit form. This was the inequality, and this is the explicit form of the first term. And let's also organize PV and QV terms, right? Since we know what PV and QV is, they can also be written like that, right? And so it will be beneficial for us to restate the problem, what we're after. We know that second condition is true, and we want to investigate if such X matrix exists such that this inequality, we are referring to the inequality, okay, this inequality holds. All right. Okay, so let's investigate that inequality, right? We know that is true, that's correct. So let's investigate if such X exists such that this inequality holds. And basically we are organizing second and third terms, all right, in the inequality, and let's distribute X terms here. This is what we have. Okay, let's continue. Yeah, let's also multiply the matrices given here. Okay, like these are like straightforward derivations, and then we know that second condition is true, and we want to investigate if such X exists such that this inequality holds. All right, so we are reshaping the problem, right? Basically reshaping the condition that we are trying to obtain, basically. And let's once again state the transformation of X, and that transformation gives us the Y matrix, right? And let's focus on that expression, and let's write that explicitly here. And this matrix is given as Y, which is partitioned as Y1, Y11, Y12, Y21, Y22. All right, so by using this equality, let's substitute that, okay, in the given inequality, and this is what we have now. So let's once again, I understand if you're like, hey, why are you restating the same problem? Like, to be honest with you, it was kind of hard for me to, it took some time for me to get the idea of the, or how to prove the stated lemma, right? So that's why I'm kind of stating the same idea, because it is it's kind of hard to, I don't know, get lost in the, proof section of the book, Duan and Yu. I'm not saying that they, I don't know, they were not straightforward. They were extremely straightforward. However, like, if you're not like extremely familiar with the proof techniques, like, these are the type of things that you wouldn't find yourself enjoying, basically, right? So let's, after that rant, let's state that, and we know that second condition is true, and we want to investigate if such y exists such that this inequality, and this inequality we are going to investigate, right? And let's just gather all the terms, and we have that. So we now, once again, we know that second condition is true, and we want to investigate if such y matrix exists such that this inequality holds using, and by the way, I mean, A, B, C, D, right? And we are familiar with Schur complement, and right, this is Schur complement. Or you can also write D is negative and A minus B, D inverse C negative. Right, this is Schur complement. And by the way, this is if and only if, right? So no conservatism there. Okay, let's continue. We want to investigate if such y matrix exists such that this inequality holds. Okay, by using Schur lemma, and here in that lemma, the partition is can be expressed like that. And all right, this is Schur lemma. I'm not gonna like talk much about it. We already know what it is. Right? It's like, if you're kind of dealing with, or if you're even have a little familiarity with the LMIs, and maybe in contour, okay, you know what it is. Okay, so, well, now the problem can be stated as, we know that the second condition is true, and we want to investigate if such y exists such that these two inequalities hold, right? So let's focus on the first inequality, because y, and I don't know if you can see that, but it is easy to see that such y exists no matter what, right? But before that, since h bar, and this is h bar, and since h bar is stated here, we first need to focus on the first inequality, and we want to prove that such y11 exists such that h bar is negative. If we are able to do that, like, second condition is like, there is nothing to prove. Okay, of course, such y12, y21, y22 exists, because, yeah, it's by choosing appropriate y terms other than y entries, other than y11, okay, this condition can hold. All right, so let's state NP and NQ, meaning right orthogonal complements of P and Q respectively. So they can be given in terms of the entries of V matrix that we used in a moment earlier. So, well, this is V transpose H and V. This is like H matrix transformed by V matrix, basically. And this is the explicit term, right? We are not deriving anything. We written that already. So let's look at this expression. Let's look at this expression, because that expression is this, right? And if we derive the terms, we would have that. And by the way, here's the thing. Like, intuitively, that might come as a, yeah, that makes sense, right? However, like, in the appendix section, and I just written a little MATLAB code and to demonstrate that idea, right? And that kind of, okay, to be honest with you, it was kind of hard for me to understand. Okay, that is correct, hence, or that implies that, right? Or let me just, that implies that. That was kind of hard for me, right? And we're just like deleting them, and because of that, we have ended up like zero terms in these entries. It was, I don't know, it took me some time to get that. All right, let's focus on this, and we know that that is negative, right? And using that expression, we know that expression, or this, smaller matrix is negative. Okay, the same idea can be, okay, this is what we know, and again this is NQ, right? And this is what we have. Okay, so we know that is that's correct. So by just deleting them, we have ended up deleting these terms. All right, that wasn't obvious to me. Yeah, and the result is this, right? Okay, if and only if that expression. So now, 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 we used to say, okay, we know, NP and NQ terms, NP containing inequalities, and now we're going to say, we know that, like, these two inequalities, and now we want to investigate if such Y matrix exists such that this inequality holds. And okay, using the following lemma, and a Z matrix, which is partition here. Okay, then there exists a matrix X such that this inequality, if and only if these two inequalities. Okay, so if we know that is correct, we can always find an X such that this like larger inequality holds, right? That's the idea. And if you have a nice, like, strong photographic memory, you can detect that, yeah, that expression and that expression, they're like really similar. So, and we also know that this and this, like, for this problem here, look at that, for this problem, this is something that we know, and if and only if that expression. So by using that lemma 2.10, which is again in Duan and Yu's book, and this inequality holds. Basically, we can state that. All right. So in conclusion, such Y11 exists. For the second inequality, it is easy to see that by an appropriate choice of, like, other entries of Y matrices or Y matrix, second inequality holds, right? Okay, therefore, and this will be the final sentence, I guess, therefore such Y exists such that the aforementioned inequalities hold, and therefore such X exists such that the first inequality holds. Okay, really means like we're done with the proof. And okay, let's focus on this, like, little MATLAB code. And V matrix was V1, V2, V3, and V4, right? Okay, and this is, imagine n equals 4, right? R 4. So H is like m by n, and in that case 4 by 4. Okay, So instead of writing v1, we just written 1 1 1 1, and for v2 2, v3 3 4. Okay, let me just fill out the spaces. Okay, this is V matrix. All right, let's transform the H matrix, which is, what was it? Yeah, this is just, H is like 7, like all the entries are 7. Okay, so this is this expression, right? And let's continue, let's focus on v12. What v12 is, like v12 is v1 v2 and other entries are 0. Okay, 0 vectors, we just changed those, right? v3 and v4, we just changed those. And now let's look at that, okay, what do we have? We have that, we have this. So if you can see that they are similar, right? Yeah. So, and also let's look at v13, which is v1 0, v3 0. Okay, and v13 transform H by using v13 matrix, and this is what we have. And let me just delete that, like 112 336, right? 336 1008. Okay, like other terms zeros, right? Okay, so I don't know, I just edit this MATLAB code, so yeah, let me just show that part yet. Yeah, this part was not obvious to me. Yeah, this is what we have, and this term can be written like that, right? And this is what we have in the second part. This term can be written like that. And if that wasn't obvious to you, by using the in the append, by using some little MATLAB script, yeah, you can, I don't know, trick yourself or make yourself believe that is the case, right? Okay, so that's all. In the following videos, hopefully I will be proving other lemmas in chapter 2 of Duan and Yu's LMIs in Contour book. And thank you, and don't forget to subscribe, I guess.